Hello and welcome to Lecture 3 of Magnetic Fields of Moving Charges in Phys 1204. At the end of the last video lecture, we saw Ampere's law in a nearly complete form. We'll finish writing down Ampere's law in this video lecture and then see a few examples of how to use it to calculate fields. This is the form that we've seen for Ampere's law. We know that the line integral around any closed path is the same for any path that encloses some current, and it's proportional to the current. So to have a complete form of Ampere's law, all we need to know is what the proportionality constant is. This is just like the point where we had Gauss's law, and we just needed to know what the proportionality constant was, and it turned out to be 1 over epsilon naught. So I'm just going to give it a name at the moment. I'm going to call it mu naught, which is the magnetic constant. It goes by some other names, such as the magnetic permeability of the vacuum and various other such names. And now let's talk about what it is. So let's look at this new magnetic constant. We haven't seen this before, and before I talk about the value of it, let's look at what its units must be. So on the left-hand side of the equation, the units we have are teslas times a distance, so Tesla meters, and that is equal to mu naught times a current. And so that tells us what the units are of mu naught. It is apparently Tesla meters per ampere. Now, the value of it might strike you as a little curious because you're used to these sorts of physical constants, and they're generally things that are measured, and so they come out to some, rather arbitrary seeming set of digits because they're just something that's measured and the actual value depends on our choice of units. However, mu naught has a value which is exactly 4 pi times 10 to the negative 7 Tesla meters per ampere. And note that because it is exactly 4 pi times 10 to the negative 7 Tesla meters per amp, that means we know it to infinite precision. And that tells you that this is not a measured value. This is, in fact, a defined value. In the next lecture, when I talk about the definition of the unit amperes, it'll become clear why mu naught is a defined constant, not a measured one. There's an important sign convention for the encircled current by a path. Let's think about this current that's coming out of the page. You know from right-hand rule that the B field due to this current will be circles which go around counterclockwise in this perspective. And this path that I've drawn is also going around counterclockwise. And so that tells you that the path into the line integral is going to be greater than 0 because everywhere we are on this path, the B field and the length element are parallel and in the same direction. And so that tells us that this I will give a positive encircled current. On the other hand, if we go the other way around the path, now our length element is always in the opposite direction to the B field, and this is going to make the line integral negative. And so that tells us that our encircled current must now be, in our sign convention, negative. The reason this matters is that sometimes you have more than one current going through your path. So, for example, here is a path going around 2 wires with currents running so that one is going down through the path in one direction and the other is coming up through the path in the other. Now, if you notice, what we concluded up here was that if there was a right-hand rule connecting the way we go around the path and the direction of the current, then we get a positive line integral. So here you want to compare these by right-hand rule. And if you stick your thumb of your right hand along I2, you'll find that your fingers are curling around in the same direction as the path. Whereas if you stick your thumb along I1, you'll find that your fingers are curling around opposite to the direction of the path. And so this tells us that our total encircled current is going to be I2 positive minus I1, or in other words, negative 2 amps. So the rest of the lecture is just going to be a couple of examples showing how to actually use Ampere's law to calculate fields. So first I'm just going to lay out a general strategy. You should start by sketching the current distribution and the expected shape of the magnetic field. And now you need to choose the shape of an Amperian path. So just like it was crucial when we used Gauss's law to think about the shape of our Gaussian surface, we now have to think carefully about our Amperian path. And some general guidelines is that if the B field lines are circles, then you should choose a circular path. And if the B field lines are straight, then you should use a rectangular path. The idea is that you want to position the path so that everywhere you look, the path is either parallel or perpendicular to the B field, and you want the B field to have a constant magnitude along any given segment of the path. This will make the calculation easy. So let's use Ampere's law now to find the B field due to the simplest thing we can, which is a long straight wire. And as usual, when I say long, what I really mean is infinitely long. So in other words, the ends of this wire are far enough away that we don't need to worry about it, and we can just treat it as if it was infinite. So we need to pick a Amperian path. And we already know that the field lines make circles. And so we want a circular path. So I'm just going to pick an arbitrary circular path around the current. And I'm going to choose to go around it in the same direction that I know the B field points. So in other words, the direction around my path agrees with the direction of the current by right-hand rule, and so by the convention, the encircled current is positive. And so now I'm just going to write down Ampere's law, where that is the encircled current. It's just the current we're talking about here, which I've called I. And by the choice of a circle centered on the current, I know that the B field is parallel to the direction I'm going around the path everywhere. And so B dot dl is just B dl. And I know that the B field is the same everywhere on my path. And so I can just pull the B out of the integral. And so I just have, and that integral of dl is nothing more than the length of the path. So if my path has a radius, which I might as well call r, then that is just 2 pi r. And there, I have the strength of the B field as a function of distance from a long straight wire. And so we see that the B field drops off in strength as 1 over r. Now, I'll point out, in deriving Ampere's law, I actually assumed that the B field falls off as 1 over r. Or rather, I said experimentally, it's easy to show, and it is. So if we had got any other answer, we would know we've done something wrong, because we would have got an answer that disagrees with our original assumption. It's important to note that this result only applies to a infinitely long wire, and I think it's useful to see why the argument only applies to an infinitely long wire. Note that if this wire isn't infinitely long, then at some point we have to have other wires that head off from it, something like so, and presumably somewhere there's a battery or something, which is the reason there's a current in this wire in the first place. But now think about this point and this point. This point is closer to these wires than this point is, and so the strength of the B field here should be very different from the strength of the B field here. But to get this result, we had to assume that the strength of the B field was the same everywhere on our path. And so if our wire isn't infinite, and that means there must be other wires nearby, otherwise how did we get the current in this wire, then the whole argument falls apart, and we can't do this, and this isn't the correct expression for the B field strength. Let's check whether you understand the sign convention. So here is a sheet of metal, and it has a current flowing in it, and the current in the perspective drawing is supposed to be suggesting that the current is coming out of the screen. And I've drawn an Amperian path, and you just have to decide whether the enclosed current is positive or negative.